Hello and welcome to this lecture. In this lecture, we'll start looking at a very important concept which is called limit of a function. Okay. So, we've seen limits of sequences and this is limits for functions. Okay. So, it's a slightly different version. We've also seen functions, we've also seen sequences, we've seen limits for sequences. Now, we're going to see limits for functions. We'll see it's an interesting combination of the notion of sequences and functions which gives us limits for functions, and that's very useful. What is it useful for? For one, you recall the second problem that we did, that we used as motivation for why we should study limits and all that. That's basically plotting and continuity of function. Okay, so when you look at a function and when you want to plot it, you take a few points and then you sort of join it smoothly. Okay, so what is the smooth? What does that mean? What exactly is the meaning? Why is it justified in most places, etc.? All of these things come from this notion of limit of function. Limit of function is very useful. It's a very important ingredient in defining smoothness. Okay, so without further motivation, we can jump into this topic and figure out what this limit of a function is. Okay. So here is sort of what I said. We're going to put together the notions of sequence, limits, and functions. So let's do that slowly by looking at a smooth function, what we think of as a smooth function, and something soon enough I will introduce, which is a non-smooth function. So we'll compare smooth and non-smooth and ask a very good question about sequences and limits and how the function connects all of them together and how to look for notion of smoothness in function. So that's what I'm going to do now. This is just a motivation before the actual definition comes in. Okay, so here is a smooth function f of x versus x, and in particular, this is smooth at x naught. What do you mean by at x naught? So if you look around x naught, it is smooth. Okay, so in some sense, around x naught it's smooth. The whole function maybe is smooth. Okay, that's all right, but let's say around x naught, a particular value x naught, it is smooth. So because the notion of smooth is a very sort of around a particular point, isn't it? I mean, of course, it may be smooth everywhere, but then I want to first say whether it is smooth around one point before I can say whether it's smooth everywhere. Okay, so first I'm going to focus on one particular point, x naught, which for this function f of x, the function value is f of x naught, and that is marked in blue here on this curve. Okay, around x naught, what do I mean by saying things are smooth? Okay, so that's the question I want to ask and sort of figure out what is the meaning of that and what some intuition around that before we define these limits and notions clearly. Okay, so here is the important connection to sequences. What I'm going to do is I'm going to think of a sequence an which converges to x naught. Okay, so the limit of this sequence, some sequence an, whatever it may be, right? So, but what property does it have? In the limit, it goes to x naught. Are there going to be sequences like this? Yeah, it is easy to construct sequences like this. For instance, you can say x naught plus 1 by n, right? Or x naught plus 1 by n squared, or anything else that converges to 0, right? So those kind of sequences will have this property that the limit of this sequence as n tending to infinity is going to be x naught. So, what am I doing here? I'm just looking at a sequence which on the x-axis is going to converge to x naught. Okay, so here is a way to visualize that. So you say what will happen to this sequence an when n becomes very large, the values in this sequence, they will sort of congregate, the points of this sequence will congregate around x naught, right? So they will sort of collapse around x naught, because I know as I go to a larger and larger n, I cannot be too far away from x naught, right? Because I'm converging to x naught. Because of the convergence, all these red dots, which are values of an, actual values of this sequence for large n, they're going to be around x naught. Okay, so here is the little trick or little notion which is very crucial here. What we do next is we look at f of an for large n. Okay, so here are my an for large n, these red guys. Okay, I've shown just a few of them. Okay, I can now look at f of an. Okay, what will happen here? I go to the f and then look at this guys, and these guys are sort of congregating around f of x naught, isn't it? So when an is converging towards x naught, these f of an also seem to be congregating around x naught. They're all going closer and closer and closer. Okay, so that seems to be an interesting property of a smooth function. when this f is smooth, this congregation seems to happen. Now, to be sure of making this kind of an idea as the basis for smoothness and continuity and all that, we should also look at a non-smooth function and see what happens in this same case. Okay, so that's what I'm going to do next. Okay, I'm going to take another function g of x which has some discontinuity or a jump at this same x naught. Okay, so here is an example of this guy. It's going all smooth till x naught, and then at x naught something happens to it. It decides to jump, and it sort of jumps at this x naught itself to this higher value, and then proceeds from there after that very smoothly. Okay, so this is this function g of x versus x. Is that okay? So this graph is fine. And what have I done here? Why have I put this white circle here and then this red thing here? This is basically, see, what happens is any function for a particular x naught has to assign only a single value, right? It cannot give multiple values. So when I have two lines cutting like this, I have to tell myself which is the actual value of the function. So in this curve, this value is not the actual value at x naught. That's why I have put an open circle here to show, this is not a value. And here this solid circle indicates that this point is actually the value of g. Okay, so be very, very careful when you show a function, when you show a jump in a function, you always have to indicate at that point where the jump occurs which is the value of the function. But it could be 2, but both are not possible, right? Function can assign only one value to a input. It cannot do more than one. Okay, so you have to say clearly which one is it, and that I'm doing by this blue dot indication. So that's why I've done here. Pay attention to this. This is something I may ignore later on, but you should always remember that when there is a jump, only one value can be assigned here. Okay, so you have to figure out which value it is. Maybe something in the middle also you can assign. I mean, you can assign any value, but I have put this value here for convenience. Okay, okay. So this is a function with a jump. This was a smooth function. We observed something about sequences and convergence here in this smooth case. What happens here? Let's see that. We can do the same thing, right? We can take our same sequence an, right? Because that is also converging to x naught here. And then ask this question, what happens to g of an for large n? And notice what happens here. Because of this jump discontinuity here, and when I go from this an which is tending to x naught, which is converging to x naught, some of the an which happen to fall to the left of x naught end up away from g of x naught, and some of the an which are going to fall luckily to the right of x naught, they end up near my actual g of x naught. Okay, notice this separation here because of this jump discontinuity, and that separation here is not there because of the smoothness. Okay, so looks like this idea of taking a sequence tending to x naught and looking at what happens to it when that sequence is hit with this function f for g, and then seeing if there's a separation or not, could capture the notion of continuity very, very nicely, right? So notion of smoothness in the function, whether there is a jump or not, is being captured very succinctly and cleanly by this phenomenon. Okay, so keep this in mind as we define the notion of a limit of a function. You will see the sequences tending to that point x naught will play a big role, and that is something we're going to use. So basically, the behavior of the sequence f of an, okay, when an is converging to x naught, is very vital and important for capturing this smoothness property for the function. Okay, so this motivates the definition for limit of a function and continuity of a function. Okay, so here's the definition. It's a bit of a long definition. It's motivated very much by what we saw in the previous slide, but let me just quickly read through this definition for you. Okay, a function f is said to have a limit L at a point x naught if the following holds. What is the condition? For every sequence, okay, so let me underline this every already for you. For every sequence an with limit x naught, okay, basically what do I mean by limit x naught? Limit as n tending to infinity an equals x naught. We have to have, it should hold that the sequence f of an has limit L. Okay, so an has limit x naught, not just any one an. It's not enough if for one an with limit x naught, f of an has limit L. That's not what this definition is saying. For every an, every possible sequence that you can cook up or that exists with limit x naught, if you hit that sequence with f, if you make it f of a n, f of a n, f of a1, f of a2, etc., that sequence, that guy has to have the same limit L. Okay, in that case, we say that the function f itself is said to have a limit at a point x naught. Okay, I hope this definition is clear. There are lots of lines here. I've underlined what is important. When do we say that f has a limit L at a point x naught? If every sequence, every possible sequence that can converge to x naught, if you hit that sequence with f, you should get, for that new sequence f of a n, you should get a limit of capital L, and that should be the same for every possible sequence a n. I keep repeating this, every possible sequence a n. There's a reason for it. That's what makes this definition very, very important. Okay, I hope this is clear for you. It's sort of motivated by the previous definition of comparison of two different cases and what happens to a sequence converging to x naught under two different cases. Okay, so you saw that in the jump case there was no limit. In the continuous case there was a limit L. Okay, now here is a notation. Okay, this is a new notation. For the first time we are using it. This is limit of a function. Okay, so we write like this. We'll say limit as x tending to x naught f of x equals L, and that denotes that f has limit L at x naught. Okay, so notice this definition. I've sort of encapsulated here. This definition doesn't talk anything about sequences. This notation doesn't talk about sequences, and sequences are not relevant for this definition, because for every sequence a n with limit x naught, this has to hold. So I don't need to mention anything about sequences here. So this notation is just a limit of this function. So this kind of thing is called limit of the function. Limit of the function f of x as x tends to x naught. That's how you read it. Okay. So you'll hear people talking about f of x tends to f of x naught, or f of x tends to L as x tends to x naught. So just like we spoke about limits of sequences, you can talk about limits for functions. For any function f of x as x tends to x naught, what is the limit? That is answered by this definition. Okay. Every sequence has to have a limit L. Okay. Now, closely associated definition is one of continuity. A function f is said to be continuous at x naught if this limit should exist, and this limit should be equal to the value of the function at that point, f of x naught. Okay. So there's a lot of things to see quickly in a definition. Maybe the definition was well motivated before. This notion of continuity is sort of surprising or very intuitive, right? You have a function f of x. It is tending to some value, some limit L around x naught. And if you define f of x naught also to be that value, if it ends up being that value, then the function is actually continuous. Okay. So this captures the notion of continuity, captures the smoothness of the function, the fact that it doesn't have any jumps or anything like that. It is smooth. Okay. So I'm going to show a whole bunch of examples and go back and forth and argue and unwrap this definition for you and show you a lot of illustrations. But nevertheless, one of the abilities in mathematics as you grow and mature is to be able to read a definition and understand it. Okay. Quite often, a lot of people get mixed up in the definition itself. They don't pay attention to some things. They pay too much attention to something that doesn't matter. But usually in the definition, you will say everything matters. You have to read very closely and make sure that you understand every line carefully. So there's a good exercise for you to read through the definition and understand. I think it's reasonable and complete in some sense. Okay. So let's see some illustration. Let's go back to our wonderful illustration of continuous versus jump discontinuous. So we had our function here, and this is just a graph, and you can sort of see that if I have a sequence going to x naught, the f of x a n also will go to f of x naught. I'm not proving anything here. It's just an illustration to show when the function is smooth at x naught like this, you will have the limit as x tending to x naught f of x be f of x naught. So it's sort of easy to see. It's just an illustration to show that if it's smooth, then this is likely to happen. Of course, you have to prove it. Okay. But looks like, if it's smooth graphically, illustratively, this is happening. So f ends up being continuous at x naught. Okay, so this is the easy case. So notice what happens here when there is a jump discontinuity. So there is a jump. So this function, it starts off from here, it comes to g1 around x0 and then it jumps off to g0 at x0 itself and then continues from there. So this is the function here. What happens when you have a jump discontinuity? From this plot, we should be able to clearly infer that g is discontinuous at x0, right? It cannot have a limit at x0. It should be discontinuous. If it is not, then I think something is wrong with that definition, isn't it? Turns out you can. Look at this sequence an. Okay, an is x0 plus 1 by n. Okay, x0 plus 1 by n. Where will be the values of this sequence for every n? It will be to the right of x0, right? Very important. But still, because 1 by n is tending to 0 here, x0 plus 1 by n will tend to x0. Okay, so here is a sequence which is tending to x0. What am I going to do? I am going to hit it with this g and ask what will happen. Okay, if as I come here, right, x0 plus 1 by n, if I hit it with this g, I am going to go towards g0, right? This is again graphical. This needs proof. I have to prove it, but I am not proving it here. I am just going to graphically sort of assume, because this an is tending towards x0 here, somehow this graph is such that g of an tends to g0. It cannot go below g0 in any case. That's the point I want to illustrate here. There is no way it can go below g0, right? It will go and be at g0. Okay, it will tend towards g0. On the other hand, here is another sequence bn, which is x0 minus 1 by n. Now, interestingly, this also tends to x0. Okay, x0 minus 1 by n. But very, very interestingly, all the x0 minus 1 by n are to the left of x0. So, whatever I do, I cannot go above g1. Right? This g of bn maybe tends to a g1, maybe tends to something else, or maybe doesn't tend at all, but it is definitely bounded by g1. So, this g of bn ends up being bounded above by g1. This g of an is bounded below by g0. Okay, forget about even the tending, right? So, maybe it tends, maybe it doesn't tend, but it's at least bounded clearly. So, once you have these bounds, that g of an is greater than g0 and g of bn is less than g1 in this kind of a picture, right? Supposing this is the picture like that, then you clearly see limit as x tending to x0 g of x does not exist, because there is one sequence for which the limit has to be, if it exists, has to be above g0, and here is another sequence for which the limit, if it exists, has to be below g1, and this is not going to happen. Okay, so limit as x tending to x0 of g of x does not exist. So g ends up being discontinuous at x0. Okay, so you see this nice rigorous way to capture a jump. Okay, so when does a function jump? It can be captured very effectively by this definition of continuity. Okay, we look for sequences and their limits. What happens to those sequences that converge to a particular point, and what happens when you hit those sequences with the function? Does it converge or not? And does that happen to every possible sequence? And this is the same. That question captures this continuity really, really well. Okay, so I hope this is a good enough illustration. Later on, we'll see how to compute these functions and limits and all that. Right now, we are not seeing computation, it's just the intuitive understanding of this definition. Okay, just for curiosity's sake, historically, this definition took a long time coming. Okay, so that's why the definition itself is interesting in its own way. Okay. So here are some other examples of discontinuities. A lot of functions and graphs show discontinuities. Here is a function which I call sine of x. It's also called signum of x. It's a very popular function. Basically, for x less than 0, it is minus 1, right? Sine of x. And if x greater than 0, it is plus 1. So this function always has a discontinuity, jump discontinuity at 0. It jumps from minus 1 to 1. So that is that property. Here is another very popular function, 1 by x, which has this behavior, right? We just now saw. And it has a discontinuity at 0, right? At 0, to the left of 0, things are going off unbounded minus infinity. To the right of 0, things are going unbounded plus infinity. So at 0, it has discontinuities. Notice curiously, both these functions, if you leave out 0, if you take any other point like 1 or 2 or something, they are all continuous there. This function is continuous at 2, right? At 2, it has no jump. It is straight. Okay. Likewise, this function at any point like 5 or 4 or 3, anywhere else, it is continuous. It doesn't have any jump. Only at 0, it shows this weird behavior. It goes from minus infinity, jumps off to plus infinity at 0, from minus to plus. Even here, from minus small number to plus small number, it jumps from minus 1 to 1. but nowhere else it jumps. Okay. So many functions will have this kind of a property. If you look at the graph, there will be discontinuities only at some specific points, not everywhere, right? And they will usually be, most functions that are useful in life will have a lot of continuous points and maybe some jumps or some discontinuities of this nature. Okay. So let's go to this function floor of x. What is floor of x? If you have like 1.5, it's like sort of rounding off. You drop the fraction part and only keep the integer part. If you have a number like 1.414, floor of x is just 1. If it is 7.5, floor is 7. Even if it is 8.99999, floor of that is 8. Okay. So you just drop the fraction, keep only the integer part. Okay. So that is floor. And here is a plot of the floor function. You see that it has a lot of discontinuities at integer points, and it has exactly at every integer point it is discontinuous, right? If you think about it, if you go from 1.99999 to 2.00001, it has jumped from 1 to 2. At 2, it has a discontinuity. Like that, at every integer it does a discontinuity. If you do a plot like this, you can quickly see the jump just by eyeballing. You can see, okay, there is a jump here, jump here, jump here. Anytime there's a jump, there's a discontinuity, and you can identify. So this is like a jump discontinuity. Here's another interesting function, 1 by x minus 1 whole squared. Okay, so it's sort of like 1 by x squared shifted to the right by 1, right? So 1 by x minus 1 whole squared, and its curve is looking like this, and you can quickly see there is an infinity point here. Anytime a curve is hitting infinity, a red alarm should go out, right? So that's like a point of discontinuity. Anytime there's a jump, there's a point of discontinuity. So this is where it is. And here is another function, 2x by x squared minus 1. It turns out it has 2 points of discontinuity. See, x squared minus 1 is x minus 1 into x plus 1, right? So at plus 1 and at minus 1, it jumps off to infinity. Okay. So you see here, at minus 1, it's going off to minus infinity. Then to the right of minus 1, it is coming down from plus infinity. Same thing happens at plus 1. To the left of plus 1, it goes off to minus infinity. To the right of plus 1, it is coming down from plus infinity. Okay. So here there are two discontinuities, one at minus 1 and one at plus 1, wherever this denominator goes to 0. Okay. So here is another function, piecewise continuous, piecewise definition. Okay. So these are very, very common, particularly in signal processing and many applications in electronics. Many functions will be defined piecewise. For x less than 0, they will be 0. Okay, this function is 0. And for x greater than 0, it is 2 power x. So it starts off at 1, no? It goes off to, exponentially fast for the right hand side. Left hand side is 0. So you see that jump here, right? This jump here immediately shows you the discontinuity. So if you look at the graph, there are various ways to easily identify discontinuities. Okay. Are there other type of devious things which you can't quite see in the graph? Turns out there is. Here is an example. Okay. So here's an example of what's called a removable discontinuity, which you don't quite see in the graph, but it is very, very important. Here is a function here. Notice I've defined it in one curious way. It's 2 power x minus 1 divided by x when x is not 0. Why should I say x is not 0? When if x is 0, I can't divide by x, no? I'll get a, if x is 0, 2 power x minus 1 is also 0, x is also 0, so I have a 0 by 0 form. So I don't know what to do when x becomes 0. So that's why I put a question mark here. Okay. At x is equal to 0, I have the 0 by 0 problem, and I don't know what to do with f. Okay. But the function is 2 power x minus 1 by x, and x equal to 0 alone is a problem. Everywhere else it's okay, right? 2 power x minus 1 by x, everywhere else if you plot it, you'll be okay. The question is, what about at 0? Can f be continuous at 0? Is there a limit for this guy as x tends to 0? Right? That's the question we are asking. Alright. Can you find limit as x tends to 0 of this function f of x? If you can find it, then f of 0 can be defined to be that value and you can make it continuous. Okay. So that's why it's called a removable discontinuity. Okay. If this function has a limit at 0, you simply assign f of 0 as that value and then the continuity goes away. But the question is, does it have limit at x equal to 0? Okay. It's not clear at all, right? So the first thing when you should do when it's not clear at all is try to plot the function. So I went to Desmos and plotted this function, and you notice here from the plot, you don't see anything, right? Around 0, it almost looks continuous, right? 2 power x minus 1 by x, look at that. There's nothing. You don't see anything. There's nothing going off to infinity. There's no jump. You can zoom in all you want, okay, you will not see anything, okay, there will be no scale issue here. In fact, if you compute for some values, here the some values I've computed, when you jump from minus point small number to plus small number, nothing seems to change here. It is just going on smoothly, like there is nothing going on, okay, right. So, this suggests something very different from our usual notion of discontinuity. No jump, no going unbounded off to infinity, but still there is some issue here with at 1.0, 1 point alone seems to be some 0 by 0 confusion, okay. So, it turns out these kind of cases you need to do some analytical methods and compute the limit, and the limit in this case can be computed to be what is called natural logarithm of 2. Okay, we have not seen logarithm at all in this class. You may have seen these things before, so I'm reminding you of what it is. It turns out limit as extending to 0 of f of x is equal to 0.693 in this case. So, once you know that as extends to 0 f of x as a limit, what will I define this question mark to be? Right? What will I define this to be? This guy is going to be 0.693 which is ln 2, okay. So, once I define it to be that, I know that my function will be continuous, and I have removed the discontinuity, okay. So, removable discontinuity if continuity can be obtained by assigning a value for f, okay. So, it is a very vague definition, it is not a proper definition, we will define it later. It is just to give you a sense of what it is. Okay, so if by assigning a suitable value for that point, for f at that point, you can make it continuous, like in this case, then it is called a removable discontinuity. In this case, it's happening. Another very famous example is sin x by x. I didn't want to introduce trigonometric functions in this lecture, so I didn't quote that definition. But a very popular example is also sin x by x. Once again, it has a limit of 1. And that's also very useful, particularly in electronics, okay. So, this kind of discontinuity can also happen, all right. So, in summary, if I have to identify discontinuities for a function, I can do so from the graph, which is okay. In the graph, I have to look for jumps at specific locations, or if things are going unbounded at some location. So, this is a clear indicator. From the expression for the function, if there is a piecewise definition, you can look for jumps, or you have to be very watchful whenever the denominator goes to 0. When the denominator goes to 0, you may have a removable discontinuity which you have to establish analytically, or you may have things going off to infinity which may be easier to identify and fix, okay. So, in any case, continuity clearly depends on limits of functions, and we have to learn how to compute limits of functions. We learned how to compute limits of sequences, all those rules, and taking limit of an expression. Like that, we will approach this problem and figure out how to compute limits of functions in the subsequent lectures. Okay, thank you very much.